Hey everyone, welcome back to Stat 5616. In this lesson, lesson 2B, we will be discussing a follow-up analysis for a completely randomized design. Specifically, we'll be talking about contrast through defining contrasts and providing some examples. If we recall from our previous lesson, 2A, we were looking at completely randomized designs. And a completely randomized design is when we randomly apply treatments to experimental units, and we look to see if a treatment has an effect using a one-way ANOVA. So from last lecture, we looked at a paint example, and we said that there was no evidence of that paint having an effect on our response. So let me introduce another example called the bologna texture example to just refresh what we learned in lesson 2A, but then also motivate what we're going to be talking about today. So in our bologna example, our goal is to compare the mean texture of low-fat bologna made with soy protein isolates and cognac flour blend under different mixture combinations. Our response is going to be texture reading. So in this example, we have three treatment factors. We have the cognac blend level, flour type, and the SPI level. So again, completely randomized designs work with only one treatment factor, or we can do a combined treatment factor. And so for this example, we are going to combine these levels to get 12 treatments. How we got 12 treatments was we had 2 blends times 2 flours times 3 SPIs, which gives us 12 treatments. And so we can see our data down here. We have 12 mixtures. Additionally, with each mixture, we're going to have 3 replications per treatment. So this implies that our total number of experimental units is 36 because we have 3 replicates for 12 treatments. All right, so let's do our ANOVA. The first step is to write down our hypotheses. For this example, I used the effects model, so the alphas, where we're going to see if there is no effect and then there is some difference between these mixtures. I went to jump/R to get our ANOVA table, which again, for our homework, I would expect you guys not to do this stuff by hand, but you can use your software. We can see that we have a large F value, which results in having a small p-value, the p-value over here for R. Now you might be saying, hey, these look different, but really they're not. This in jump is saying that the p-value is just super, super small, where in R, it's going to give you some machine precision type answer. Okay. And so with a p-value less than 0.0001, we will reject the null hypothesis, saying there is a sufficient statistical evidence to conclude that the mixture has some effect on the mean texture of low-fat bologna. So unlike the highway paint example that we saw in lesson 2A, here in the bologna mixture, we see that we have a difference. The difference of mixtures has an effect on the texture. And so now that we know this, we may want to do some follow-up analysis to decide which of these treatments actually has an effect. One follow-up analysis is called a constraint or contrast. It's called a contrast. Ooh. A contrast is going to represent a single possible elaborate comparison among population means. So contrast can be used to test the significance of an individual comparison between the levels of treatment factors that we're interested in exploring. So for example, in our bologna example, we may want to compare the average texture reading for bologna made with different cognac blends. So that is, we might want to look at the difference between these 6 and these 6. And to foreshadow, we will do that example towards the end of this lecture. Okay, so we can do contrast when we have a specific contrast that we want to compare. Before we go into super details and doing the analysis, let's introduce some notation. So the population contrast is a comparison among the treatment means. And so we denote the population contrast by just having L. Okay. And what it's going to be is it's going to be a linear combination of our parameters. So we see some CI. This is going to be our constraint coefficients. And then we have our treatment means. The key here is that our constraint coefficients must sum to 0, i.e. equals 1, TCI equals 0. Okay. Again, this is just fancy notation to say that the constraints are linear combination of our treatment means. We can also write this in terms of our effects model, and that's how we would write it here. Okay. So again, as a note, contrasts are typically used to address a specific problem the researcher is interested in, and they should be planned before collecting the data and performing the analysis. So let's go to a non-bologna example just to get some intuition behind this. And so let's say we have test exam preparations that we want to compare the effect and see if two treatments differ. So we have no prep, we have prep A for studying for the exam, we have a prep B for studying the exam, and we have a prep C. And there could be a bunch of different hypothesis tests that we would be interested in, and we're just going to focus on this one right here. And what this one's going to do is it's going to try to help us figure out is there a difference in test prep for C versus B? Okay, so C versus B. Our hypotheses would be there is no difference, and our alternative would be there is a difference. How we would write that in contrast form is mu B minus mu C, because with contrast, we want them all on the same side. Another way we could write this is mu C minus mu B. Okay, you could write either or. So in this specific contrast, where we are comparing these two groups, we want to find or identify what our contrast coefficients would be. And so in this case, if we were looking at the mu B minus mu C, our constraint coefficients would be 0, would be mu of no prep is equal to mu of A, which is 0, because they're not part of this. And then our mu of B is going to equal 1, that's a positive 1. And our mu of C is going to equal minus 1. Again, they need to sum up to 0. If we were to do this green example, our mu of no and mu of A will still be 0. Our mu of B will equal minus 1, and our mu of C would equal 1. Okay, this should have been covered in Stat 5615, so I won't spend too much time here, but just getting you guys back into it. It's important that you understand the constraint coefficients and how to implement this into software, which I'll show you in one of the R or Jump videos. So far, we talked about a population constraint, but in statistics, we always have to estimate our parameters. And so let's talk about that. So to estimate our constraint, which we denote as L hat, we replace the group mean. So remember, L is equal to the sum of Ci mu I, where I is going to go from 1 to T. We're going to replace this mu I with our group mean estimate. Okay, this should look familiar from lesson 2A. So L is the theoretical equation, whereas L hat is a number we're going to get from our data. And so now we need to answer questions with these constraints. But just as a reminder, constraints are typically used to address specific questions, and they're planned before collecting the data and performing the analysis. Okay, so to determine if comparisons of mean are statistically significant, we can perform hypothesis tests using these constraints. To do this, though, we need to understand the properties of L hat. So under ANOVA assumptions, L hat is a linear combination of independent normal random variables. So L hat must also be normal, okay? This statement, the linear combination of a normal is also normal, can be proven using statistical theory. In this class, that proof is beyond the scope of what I'm teaching y'all, so you don't have to worry about that. You can just trust me. So again, our point estimate for our contrast is L hat here. The standard error for L hat is going to be represented here, in which we see input from the ANOVA table. So MSE, this is from ANOVA table. We have our number of replicates, in each group. And then we use our constraint coefficients here. Okay, here's one key though. This is for a balanced design. So this is the standard error for a balanced design. Now, if we don't have a balanced design, so unbalanced, maybe one treatment has 3 replicates and another treatment has 4, you would want to use this standard error. So this one is for an unbalanced design. And I'm noticing one thing that's going to look a little weird. This should be the sum ti equals 1 ci squared divided by n. So that n should only be part of that. It shouldn't be dividing the entire sum. Okay, so it turns out that our L hat is distributed with a t distribution with n minus little t degrees of freedom. Now, if we knew the true value of the background noise, i.e. the MSE, we would be using the normal distribution or thinking about z-scores and all that. But knowing that background noise is very impractical, so we typically have to estimate it, and so we have to use a t distribution. Our t statistic for a balanced design would be L hat minus L divided by our standard error, and for an unbalanced design, it'd be the same thing, where our standard errors matches for an unbalanced design. Typically, L is set to 0, and we're looking at these types of hypotheses. So we have one-sided or we have a two-sided hypothesis test. This is very similar to a two-sample t-test, but they're not exact. It's not exactly like a two-sample t-test because we have more than 2 groups. Even though, let's say we go back to this example, we're only comparing preparation B and preparation C. The other 2 test preparations are impacting our MSE value. And so while it seems like a 2-sample t-test, it's not exactly because our other test preparations are impacting that MSE. Another way we can look at constraints is through an F-test. Here's the thing though, F-test is only for two-sided. Okay, so a two-sided t-test will be equivalent to an F-test. And how you end up doing that is you find your constraint sums of squares for L, which will look like this. We compute the F observed, calculate the F observed, which is going to be SSC over MSE. The reason we could write it as the mean squared of the constraint, but our degree of freedom is only 1 in this case. So it's easier to look at that. And again, this is only equivalent to a t-test when it's a two-sided t-test. All right, so let's get to an example, and more specifically, let's get back to that bologna example we started class off with. So again, in our bologna example, we ended up concluding that we're going to reject our null with a really low p-value, and so there is some evidence that the mixture has some effect on the mean texture. The question we want to look at is there a difference between the mean texture reading of bologna made with the different cognac blends? So we want to, if we look back at our data, we want to look at comparing this upper group with this lower group, because here's with the blends of 0.05 and here's the blends of 1. So in order to do a simple comparison, we're going to pretty much look at the average of this group and the average of this second group. And so how we can write that as our hypotheses is by writing our null as mu1, 2, 3, 4, 5, 6 divided by 6. It's the average of those first 6 treatments. Are they equal to the average of the next 6 versus are the first 6 not equal to the next 6? How we write this in a contrast, again, you need to put this all on one side. And so we have our mu1 through 6 minus our mu7 through 12 average. Our contrast coefficients in this case are C1 equal to C2 equal to, I'm going to put dot, 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 which is going to represent C3, 4, 5, C6 is going to be equal to 1 over 6, and C7 equal to C8 equal to dot, dot, dot. C12 is going to equal minus 1, 6. And again, you could have had these flipped, so maybe instead of subtracting this way, you subtract that way, and these contrast coefficients flipped. Our hypothesis test for this is L is equal to 0 versus L not equal to 0. Why is it two-sided? Because we're just trying to see if there's a difference. So we go through our test statistic calculations. First, we need to estimate L hat. And again, this is just looking where we are now inputting our group means through here, and we're going to get our L hat of 7.65. Now, this seems pretty far away from 0, right? But because if there's no difference between these two blends or these two groups, we'd expect it to be 0. But here we have 7.65, which is pretty far from 0. Here's the key though, we need to take in account variation because this could have a large variability. And so we always need to not only look at the mean, but we need to look at the variance. And so we need to calculate our standard error. We are going to use our standard error with the balanced design because we have equal number of replicates. Let's just talk about where all these numbers are coming from. So our MSE right here, this 3 point is coming from our ANOVA table. Look back at our ANOVA table, and it's coming from here in the jump output and here in the R output. So we're going to take that, we're going to plug it. 3 is coming because it's our number of replicates, number of reps per treatment, and then these CIs are coming from up here in our contrast. If you work out all the math, you will see that our standard error for L hat is 0.58. We calculate our T observation, which is 13.8, You could do the rejection region, but we're going to use software and we get a p-value that is less than 0.0001. And so we can reject our null and conclude that there is a difference between the mean texture readings of bologna made with different cognac blends of 0.5% and 1%. Okay. Now let's just talk about what you would see if you did this in JUMP or R. In JUMP, again, watch the videos to see how we get these. This is what you would see. Here's your F ratio. Here's your p-value. Here is your estimate, i.e. your L hat. Here's your standard error. And then here's your T statistic. Okay? Now, notice we were in a two-sided test. And so if we took our T ratio, so 13.8, and we squared it, it's going to be roughly 17.378. I say roughly because of rounding. Okay? Now, to do this in R, I do have two examples right here. This is doing a contrast that we saw, so these will be the exact same. This one's going to come into play down here, so I'll talk about that in a second. So here's our L hat in R. Here's our standard error. Here's our t-value, and then here's our p-value, or our t statistic and our p-value. Okay, so they're saying the same thing. What this is hinting at is that we can take contrasts and we can multiply them by a scalar. Okay, and so down here, if we were to instead use the contrasts 1, 1, 1, 1, 1, and minus, 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 minus 1, instead of 1/6, i.e. we multiplied by 6, we are going to get the same answers. But we're going to get the same answers in terms of our t-value, our f-value, and our p-value. What's going to change, the only difference, is your L hat and your standard error will change. And let's think about that. If we come back here, when we go through our calculations, and so instead of using 1/6, we use 1, that's going to come into impact here. And so we're not having that, we're not having that. And again, it's going to come into impact here. So we're going to notice a difference in our estimates, but not in our F and P. And so what this is showing here in R is if we used the 1 and -1 constraints, our estimate is larger, our standard error is a little bit larger, but our T and our P values are the exact same. Okay. The remaining of this lecture is kind of going through the hand calculation. So again, we can notice we get our L hat, we get our sums of squares contrasts here, we get our MSE from the ANOVA table. This is key, you're getting it from the ANOVA table. You could use the rejection region or the p-value. I recommend p-value because you can use software. Again, for implementation on how to get these contrasts, watch your respected videos.